So welcome to section 11.2. We're going to discuss a particular conic section. We've discussed parabolas in the previous section. Now we're going to discuss the ellipse, which has this kind of oval shape, but it's a little bit special. You can see the shape of an ellipse in a few applications. First one is the orbit of the Earth around the sun. So the sun is at one focus of our elliptical shaped orbit, and we're actually closer to the sun in the winter on the winter solstice than we are in the summer during the summer solstice. So figure that one out. You also might see it in the shape of an lithotripter. Now, the lithotripter works by generating some energy waves in an elliptical shaped reflector. And at one focus is your electrode, at the other focus is hopefully your kidney stone or gallstone so that it can get pulverized and crushed and you can pass it without having to be cut open in a nice invasive operation. So this is a non-invasive way to get rid of those. We're going to see more about where you'll find the properties of an ellipse or the shape of an ellipse. But basically, here's the anatomy of an ellipse. There's these two special points, this black one here, this yellow one here. Those are called foci, plural of focus. And there's also another property that I'll allude to, which is kind of hinted at here with these lines emanating from the foci to the ellipse. So we'll take a look at that. But first, let's jump into graphing an ellipse. Just dive right in and work with a particular problem and try and see what we expect. I'm going to start out with a nice friendly one, x squared over 16 plus y squared over 4. And not knowing exactly what to expect, we're going to try and find our x and y intercepts. So if I want to find the x intercepts, I'll set y equal to 0. And when I do that, I get x squared over 16 plus, well, 0 equals 1. If I multiply both sides by 16, then I'll get x squared equals 16 or x equals, did you say 4? Well, I hope you said plus or minus 4 because there's really two roots there. So you got 4 and negative 4 going along with y equals 0. We'll also do the same over here. We'll set x equal to 0, try and find our y-intercepts. So that's going to give me 0 plus y squared over 4 equals 1. Y squared equals 4. Got it this time. What could y equal? Yeah, remember that plus and minus. So 0 for x can be 2 or negative 2 for y. Let's see what that looks like on a graph. So let's see, not that one, sorry. Let's come up here. And there's our graph. We can see the vertices are what we found. And then in between, we've got, a nice oval shaped curve. And what I'm going to ask you to do is do exactly what I did, which is find the vertices and then, roughly sketch in the graph in between. Now, to make that a little bit easier, let's look back at our original equation and see if we can't tinker with that a little bit. So I'm going to take this one and rewrite it. Let's take this, bring it down here and see if we can't make that a little bit more useful, because this was kind of a pain in the butt to have to do all that. And if you notice, in the x direction, we had vertices at plus and minus 4. In the y direction, we had vertices at plus and minus 2. And I think you can probably see the connection between 16 and the 4s, 4 and the 2s. To make that connection a little bit more crystal clear, let's write this as x squared over 4 squared plus y squared over 2 squared equals 1. Nice. So with that, you can kind of look at the form of this equation and realize, in the x direction, I'm going to move 4 to the left and 4 to the right to find my vertices. And in the y direction, up 2 and down 2, again, to find my vertices, this time in the vertical direction. And there's our points. Beautiful. So that's going to be a nice little shortcut for us, is to kind of rework the problem a little bit and write them in a more convenient way. Let's move on to example B here. So click over to here. We've got a new equation. x squared plus y squared over 9 equals 1. Now, if I follow my guide from the first example, then I'm going to probably want to rewrite this. Now, I can rewrite this pretty easily as x squared plus y squared over 3 squared. But what do you do about that other x there in the denominator? Well, there is no denominator. But how about if we say, well, we'll divide that by 1, giving it a denominator? And a nice little insight for you, 1 and 1 squared are the same thing. So I've got a little challenge for you. And pause the video if you'd like to try and solve it as we go through it. But I'm going to present you with two graphs. I want you to decide which one is the correct one. So are you expecting this one or this one? Which one do you expect? So we'll go back here for the first one or the second one. Well, I hope you said the first one because this is what you should expect. In the x direction, we expect vertices 1 to the left and 1 to the right of center, and then up 3 and down 3 from center. So just kind of looking at this, x and y, I should expect 1 and negative 1 as vertices in the x direction. That'll go along with 0 and 0 here. And then 0 and 0 here is going to go along with 3 and negative 3 in the y direction. If you look at our graph, that's exactly the points that we get when we look to see the vertices. So there's your 0 and 3, 0 and negative 3. But we're not going to be done with just finding those points. You've seen me mention a couple times that we're going to want to find the foci. So how do you find the foci of an ellipse? Well, I'm glad you asked. So let's find the foci. Foci will lie a distance of c away from the center, along the major axis. Okay, so, well, what's the major axis? That's a good question. Let's look back at our current graph right here. There's two axes that run through this parabola, ellipse. One is along the x-axis from this vertex to this vertex, and the other one's along our vertical or y-axis along this line, line x equals 0. Of these two, the longer one is your major axis. So we're going to have a point that represents our center. That's going to be at 0, 0. So that's the center of our ellipse. But along the major axis, in this case vertically, you're going to find the foci a distance of c away from the center. Now, I haven't told you how to calculate c yet, so let me rectify that. And let's go back over to here. When you have something of the form a squared, x squared over a squared plus y squared over b squared equals c, equals 1, c squared is going to equal a squared minus b squared, or b squared minus a squared, whichever one is positive. You could just write this with the absolute value and not worry about the sign because it'll be taken care of by the absolute value, but I just do it this way. So in our particular case, we had x squared over 1 squared plus y squared over 3 squared equals 1. So if I consider this my A and this is my B, A and B, then I'll get C squared equals 3 squared minus 1 squared, or C squared is going to equal 8, or C is going to equal plus or minus the square root of 8. Do you really need the minus? Well, maybe yes, maybe no. But what you're going to find is the vertices are going to lie a distance of the square root of 8 away from the center. So you're going to have a vertice here at 0, 3. Square root of 8 is just a little bit south of that. And then another point down here at 0, -3. And our other focus is going to be at 0 and negative square root of 8. And up here, 0 and positive square root of 8. So that's where your foci are going to be. Let's take a look at that on our graph in Desmos. And if you click down here for the foci, bam. Now, unfortunately, Desmos can't look at that and say, oh, 2.28, 2.82843, oh, that's just the square root of 8. It's not going to work like that. It's just going to give you a decimal value. You're going to have to know what that is. On an exam, I'd be expecting the square root of 8. So expect to graph an ellipse, including the foci. That's the big thing that you should be getting out of this example, and one thing that you should expect to do on an exam. Let's shut these down and get rid of the foci. Let's move on to example C. So example C, we've got x squared over 25 plus y squared over 9 equals 1. That's pretty nice. It's actually set up to work really well for us in terms of calculating our foci. Let's start out with rewriting this. This is x squared over 5 squared plus y squared over 3 squared equals 1. You should be able to look at this and pretty much tell where the vertices are going to be. In the x direction, you're going to start out at 0, 0 and move to the left by 5 and then to the right by 5. So 5, -5 go along with 0 and 0. In the y direction, up 3 and down 3. So 3 and -3, oops, all the way around. 3 and -3 in the y direction. Let's see if I can rescue myself here. There we go. Not perfect, but 0 and 0. So those are our vertices. Let's see if they match what we get when we look at them in Desmos. The nice thing about Desmos as opposed to your graphing calculator is you can click and see these vertices. So 5 and 0, -5 and 0, 0, 3, and 0, -3. Great. All that remains is to find the foci. So let's work on that. So we're going to get c squared equals 5 squared minus 3 squared. 25 minus 9 is 16. So c equals plus or minus 4. One thing you have to be careful of is drawing the vertices, the foci in the right direction. The foci will always lie inside of your ellipse. You're never going to have a foci outside the ellipse. So let's plot those foci, and they're right there. Perfect, exactly where we expected them. Notice that if I had mistakenly thought of them as 0, 4, and 0, -4, that those points would be outside of my ellipse. So a nice little check on your work that your foci actually lie inside of the ellipse. All right. So one of the other things that I'll point out, and I like to point out a lot, is that people do actually use this stuff. So several years ago in 2022, there was a mission to test out something. Now let me ask you to test something for yourself first. What was it that was the doom of the dinosaurs? What took out the dinosaurs, at least the big thing? If you said collision with an asteroid, then you're correct. The asteroid hit the Yucatan Peninsula about 65 million years ago and wiped out the dinosaurs. Now, there's currently a mission to, or was a mission to, check and see, well, if this is going to happen, what are we going to do? We can't exactly send up a bunch of space cowboys, however it was depicted in the movie, to try and take care of this. So let's see. Let's look at the DART mission. So what was going on with the DART mission is there's this asteroid that has a little satellite here, and that satellite is orbiting its parent asteroid. Now, what NASA did was try and fly a satellite right into this as fast as it could and try and change the orbit slightly. And the cumulative effect of this new orbit is supposed to help deflect where this is heading. And if this was actually something that was heading towards Earth, then they would try and redirect it so that it wouldn't hit the Earth. So that's the whole point of this mission. And one of the things that you'll see when you look at these types of missions, one of the calculations that people commonly do with ellipses is look at something called the eccentricity. So let's back up for a second and take a look at the eccentricity. So one last little calculation I can ask you to do with your graphs. I've got some examples of eccentricity here. Let me see if I can't make them a little bit bigger. Eccentricity is going to be between 0 and 1. The closer you get to 1, the more cigar-shaped your ellipse is going to be. The closer you get to 0, the closer to a circle your ellipse is going to be. Now there's a nice QR code here. You can follow that, and that should take you to a page like this, where you can actually play around with some of the properties of an ellipse. One of the defining properties of an ellipse is that any point on this ellipse, so let me move this around a little bit. Any point on this ellipse is always a consistent distance between this focus and the point and this focus and the point. In other words, if you add these two distances, and here I've called them D1 plus D2, they're always going to total up to the same thing. So watch these numbers as I let the value of W change. In other words, what point we're at as we move around the orbit of an ellipse. And the sum is always exactly 20. Now that number doesn't have to be 20 for every ellipse, but it will be consistent regardless of what ellipse you're working with. Now the shape of your ellipse is determined by the size of the axes and the ratio of those sizes. So let me shut off this for a second. And let's see if I have another demonstration here for us. Let's move on down. Here we go. So I wanted to demonstrate the shape of an ellipse in a little bit more of an interactive way. So you've got this general equation. I just, for convenience, made this 36, and I've chosen something that doesn't exactly have a center at 0, 0. This one happens to have a center at 2, -1. But regardless, the eccentricity really talks about the shape of an ellipse, and it's the ratio of that value of C to the longer side here. So I'm assuming that this is going to be the longer side, so it's going to have a length of 6. But if we change the value of A, it's going to change the shape of my ellipse. So let me scroll down a little bit. Here's the actual foci. It's going to be the length of C divided by the length of the major axis, or the semi-axis, half of that distance. And take a look here. When A is kind of small, and this ratio gets close to 1, you've got something that's almost a pencil in its shape. But as I get closer and closer to 0, then this becomes something more and more circular. Now take a look at these blue dots. Those blue dots are the foci. What's going to happen as this value gets closer and closer to 6? Those dots are going to merge in the center. And instead of having an ellipse here anymore, now I've got a circle. So what you can see is a circle is really just a special case of an ellipse. It's the case when both of these denominators are the same. So, wow, pretty cool there. All right, so back to some of our stuff here. One other little quick note here with regards to the DART mission, and that is you might have a little bit of fun if you go to Google and type in DART mission NASA. It's kind of a neat little effect that you're going to see here. So let's see a satellite flying in and crashing. Boom. There you go. So kind of funny. In any case, moving back here to, let's move down to example E. Just give me a second to copy that down. Example E is 2x squared plus 25y squared equals 50. Ready, fire, aim. Let's see what's going on with that one. Well, kind of like a lot of these, we need to start out by putting it in the right form. And that's going to mean getting a 1 on the right-hand side. Now, to get a 1 on the right-hand side, you can subtract 49. That's not really going to do it. I want it to look like this. I don't want to have a minus 49 hanging out here. So the trick is to divide everything by whatever that value is on the right-hand side. Now, it doesn't work out exactly perfect here, does it? Because when I do that, well, first one works out pretty good. That's just x squared over 25. The second one is y squared over 2 equals 1. X squared over 5 squared plus y squared over, what could I square to get this? And the answer would be the square root of 2. So you got to be a little bit clever there. Can you write down the vertices of our ellipse here? Why don't you erase me before I draw my little t-table? See if you can write those down. X and Y. In the x direction, 5, 0, negative 5, 0. In the y direction, 0 here, 0, square root of 2, 0, negative square root of 2. Great. Let's calculate a little bit more here. Let's figure out what c equals. C squared would be 5 squared minus square root of 2 squared. So it's going to be 25 minus 2 is 23. So if c squared equals 23, c is going to be plus or minus a square root of 23. I don't expect decimal values, just leave it as a nice square root. So the foci, I don't want to really put them in that table because they're not points that are actually on the graph of the ellipse, but I can put them here. Foci are going to lie along the major axis. Now, what's the major axis? Well, the major axis is the longer of these two. So let's actually look back at our graph here. And I can get rid of the foci from the previous problem. There you go. So kind of long in this direction. If a comet was orbiting this kind of an orbit, it'd be a fairly eccentric orbit. So let's see. Foci then are going to lie along the x-axis because that's the longer of these two. Of course, we could have seen that just by looking at the vertices and the denominators. So in the x direction, it's going to be negative square root of 23 and 0, and then positive square root of 23 and 0. Those are going to be your foci. Singular is focus, plural is foci. Let's add in those points. Now, they show up like this. If you did take out a calculator and check it out, you would see that that boils down to the square root of 23. Last but not least, let's calculate the eccentricity. So the eccentricity in this case is going to be square root of 23 divided by the larger of these two. That's going to be 5. So that's going to be a pretty big number. And that is pretty close to 1, I should say. Let's just do that right here in Desmos to keep it easy. Square root of 23. Hit the right arrow to make sure you're outside the square root, divided by 5. There you go, about 0.96. Let's give that a couple more decimal places, 0.959. So that's our eccentricity. Nice. And that's pretty much it. All that I could ask of you on an example like this. We will add some more stuff in section 11.4 when we start working with centers that are away from 0. But for right now, I think we're doing pretty good. Let's move on down to another kind of tricky one here. Example F. So we've got the 1 on the right-hand side, but I don't have nice denominators like I had in the previous couple. That's not what I've got. So keep in mind what I had in like the last one, where I had an x squared term over something and a y squared term over something. I had nice denominators. It's great. Same with this one. I had nice denominators. But I don't have nice denominators here, and I can't really divide both sides by 1 and expect to get anything different. So what's the trick? Well, might not be something you'll come up with right away. So let me help you out. X squared divided by 1/9. When you divide by a fraction, you invert and multiply. So you get that. And y squared over, well, can you guess? Yeah, good job. 1/4 equals 1. Now that's still not quite in the right direction here for myself, or not quite finished. So let me rewrite it one more time. X squared over something squared plus y squared over, again, something squared equals 1. Can you fill in what those somethings are? What do I square to get each of these? And I trust you're saying 1/3 and 1/2, which is great. So let's see if we can't figure out then, well, what's the vertices and such going to look like? So, nah, I'm not going to try and squeeze it in there. Let's just come down here for the vertices. Again, you can read them off in the x direction. In the x direction, we'll have 1/3 and 0, -1/3 and 0. In the y direction, you're going to stay on the vertical axis with x equal to 0. You're going to go up 1/2 and down 1/2. So kind of on the tiny side there. And when you look at the graph, at least initially, let's shut this one off and get rid of those. When you look at the graph, you see it's kind of small. So you can zoom in with Desmos. You can hit the plus key to do that, or you can just scroll with your mouse. This is kind of nice. And what you're seeing kind of makes sense. We have vertices here and here, here and here. So, okay, looking good. You see some decimal values for 1/3 and -1/3. Let's continue with a couple more things. Let's next find C. C squared is going to be, well, the larger of these is going to be 1/2. So it's going to be 1/2 squared minus 1/3 squared. So it's going to be 1/4 minus 1/9. I need common denominators there. So common denominator is going to be 36. That's going to be 9/36 minus 4/36 gives me 5/36. Okay. Which direction do those 5/36 lie? Is it going to be in the x direction or the y direction? Well, suppose that I said, you know what? Here's going to be my foci. Square root of 5 over square root of 5 over 36. Whoops. I guess I forgot one last thing here, that's c squared. So C is going to equal plus or minus square root of 5 over 36. You can simplify the square root of 36 in the denominator if you want. I don't really worry about that in a problem like this. It's just going to be a 5 over square root of 5 over 6. I don't have to have that simplified for me to get it right. I don't even think you have to have it simplified for WebAssign to get it right. That's not changing, so we'll just leave it like that. In any case, going back to our graph, what's wrong with this? Oh, yeah, we put it in the wrong direction. Your foci should not lie outside of your ellipse. So to fix that, what I guess I need to do is change this up a little bit. So let's do that. Let's make this 0, comma, square root of 5 over 36. And then likewise over here, let's get rid of that, make that 0, comma, negative square root of 5 over 36. And let's shut these two off. Those are clear. Oops, not that one. This one and this one. Those are clearly wrong. Now we're cooking with gas. So looking good. Last thing I needed to figure out is what's E, so the eccentricity. So you can take C, which is going to be square root of 5 over 6, and divide that by the larger of our axes, which is going to be the 1/2 underneath the y. When you invert and multiply, you're going to get the square root of 5 over 6 times 2 over 1, which is going to be square root of 5 over 3. And I'm not sure exactly what that number is going to be, but that's our eccentricity. Nice. Okay. Let's move on down to example G. So it says find an equation for each ellipse whose graph is shown. I'm going to start out with this one here. Maybe I'll let you do this one for homework. So example G. Now, there's a couple things I want you to notice. The first one is that it passes through the point 0 and 15. That's what this 15 is here for, is to try and tell you where the vertex is. The other thing is that it passes through point 10 and 5. Now, 10 and 5 isn't as special because it's not a vertex. That's okay. But we at least have something. We at least have that 15. So think for a second what that's going to mean for us in our equation. The fact that the vertex is at 15 and 0. What does that say I can put in here? Well, if you said 15 in the denominator, here, you're correct. So the only unknown that we have left is B. We have to figure out what B is. And here's where we're going to use the other little bit of known information. Our graph passes through the point 10 and 5. And I believe I have this set up pretty nicely on Desmos to kind of demonstrate. So let me get rid of both of those and the graph. Let's move on down to here. Let me zoom out a little bit. How come the graph isn't on? Oh, I know why, because I'm not zoomed out enough. There we go. There's our graph. Now I need to adjust B the value of B so that our graph actually passes through this point. And that's what the slider allows us to play around with and do. So if I move this value enough, then the ellipse actually does pass through this point, which is 10 and 5. So the question is, how do we find that algebraically? Because we have an approximation. It looks like it's about 6 3/4. But what's that look like in terms of a point? What's that mean for the value of B? Well, the good news is we know that that's your x coordinate and that's your y coordinate. And if I substitute in those values, I get 10 squared over 15 squared plus y squared over b squared, or in other words, 5 squared over b squared equals 1. Now, the only thing unknown in this particular equation is b. So I should be able to solve for b. That's 100 over 225 plus 25 over b squared equals 1. The lowest common denominator for something like this is 225. Let's see if I can do this a different way. You know what? I'm just going to subtract 225, actually 100 over 225 from both sides. That'll make my life a little bit easier. Now on the right-hand side, I'm going to be subtracting that from 1. Keep in mind, another way to write 1 is 225 over 225. So when I subtract that, I'll get 125 over 225 equals, on the left-hand side, 25 over b squared. It might be to my advantage to simplify the right-hand side a little bit before I play around with this some more. So 25 goes in there 5 times, and 25 goes in here 9 times. Now that I've done that, now this is a little bit more manageable. Cross multiply because you have a proportion. 9 times 25 is, again, 225. On the right-hand side, you get 5 times b squared. Divide both sides by 5. 5 goes in there 45 times. So b squared is the square root of 45. Let's see what that looks like numerically, just to try and take a quick look at it. And if you want to zoom back real quick, take a look at my calculations. There they are. So let's see, square root of 45. Come on, 45. About 6.718 or 6.708. So we were pretty close here with our slider estimate. It's just nice to kind of confirm that algebraically as well. So upstairs, you might hear my dog Aspen chirping at you. But I think we're pretty good here. This one is kind of similar. Example G here. So the only difference is that they don't actually give you, actually they do give you the vertex. So they give you the vertex here is at 2 and 0, and one of the foci is at 0, 2. So what they're doing there is they're giving you C as opposed to giving you a point and A. So they've given you A. So I'll get you started on this. So example G, x squared over a squared plus y squared over b squared equals 1. And I know that 2, 0 is a vertex. So that's telling me that I got a point here at 2 in the denominator, x squared over 2 squared plus y squared over b squared equals 1. Looking at the graph, the larger axis, the longer axis is in the y direction. That means B is bigger than A. Okay, that's good. In fact, it's necessary to notice that so that when I put this back together, try and find what B is, I know that c squared is going to be b squared minus a squared. It has to be that way because this has to be bigger than this for this to be the major axis. And so when I subtract in this direction, I'll get something positive. Now c itself is equal to 2 because that's where one of the foci is. And that's going to be b squared minus 2 squared. In other words, 4 equals b squared minus 4, or 8 equals b squared. And I guess I've solved the whole thing for you here, haven't I? Hopefully by now you remember the plus and minus for that. Although, honestly, when we plug it in, we're just going to use positive square root of 8. Looking good. All right. Hope this helps you out. If you have any questions, please reach out and get some help. There's a tutoring center. You've got my office hours. You've got other videos online. Get some help. Thanks so much.